Hello and welcome to the first video of section 3.1. In this chapter, the derivative of a function will be used to describe and ultimately to sketch the graph of that function. In this section, we are interested in maximum and minimum values on a function. More formally, a function has a local maximum at c if f of c is larger than f of x when x is near c. Now, near is a vague term. We mean that for some open interval ab around c, no matter how close the endpoints, the values f of x on that interval are lower than f of c. In a similar way, f has a local minimum at c if f of c is smaller than f of x when x is near c. When describing maximum and minimums, there is a distinction between values and points. The maximum or minimum value is the y value f of c, while the maximum or minimum point is both the x and y value c f of c. Points which are locally a maximum or minimum are referred to as local extrema. Similar to the local extrema, the absolute extrema are the absolute maximum and minimum points on f. A function f has an absolute maximum at c if f of c is larger than f of x for all x in the domain of f. Similarly, f has an absolute minimum at c if f of c is smaller than f of x for all x in the domain of f. What you would expect with the name absolute, a function has at most one absolute maximum value and at most one absolute minimum value. However, multiple points may attain these values. Take for instance the sine curve. The amplitude is 1, so the absolute maximum value is 1. No attained y value is higher than it, but the x values pi halves, 5 pi halves, 9 pi halves, and in general pi halves plus 2 pi n all attain the y value 1. In the same way, the absolute minimum value is negative 1, and the x values 3 pi halves plus 2 pi n all attain that y value. A function doesn't necessarily have an absolute maximum or minimum. Take for instance y equals x cubed. A function may have an absolute minimum, but no absolute maximum. Take for instance y equals x squared. A function may have an absolute maximum, but no absolute minimum. Take for instance y equals negative x squared. Absolute extrema are by definition local extrema. If a value is higher than all other values, it will certainly be higher than the values near it. Conversely, if a value is lower than all other values, it certainly will be lower than the values near it. The graph of every extreme value we've seen involves a hump. That is, the extrema happens at a point with a horizontal tangent line. That is not a coincidence. Fermat's theorem says to expect local extrema to have either non-existent derivatives or zero derivatives. Suppose the point c f of c is a local maximum, and assume the derivative at c exists. As a local maximum, f of c is larger than f of c plus h for h values near 0. With a bit of algebraic manipulation, we find that f of c plus h minus f of c is not positive. If h is greater than 0, then we can divide by h without changing the inequality. Since this inequality holds for h values greater than but close to 0, we can take the limit as h approaches 0 from the right. And this limit will be non-positive because the limit as h goes to 0 of the function 0 is 0. Since we are under the assumption that the derivative of f at c exists, it can be at most 0. Going back to the original inequality, if h is less than 0, then dividing by h reverses the inequality, and the limit as h approaches 0 from the left is at least 0, which tells us that the derivative of f at c is at least 0. We now have two inequalities. The derivative of f at c is at most 0, and the derivative of f at c is at least 0. Therefore, we have that the derivative of f at c is exactly 0. In a nearly identical way, it can be shown that a local minimum point c f of c, which is differentiable, has a derivative f prime of c being 0. With Fermat's theorem in mind, we define a critical number of a function to be a number c in the domain such that either the derivative does not exist or is 0. Just a word of warning. It is common for students to hear only the phrase does not exist or is 0. Be sure to note that a critical number must be in the domain. With this terminology applied to Fermat's theorem, If a function f has a local extrema at c, then c is a critical number of f. Be sure not to reverse this statement. A critical number need not be a local extrema. Take the function y equals x cubed. The derivative of dy over dx is 3x squared. X equals 0 is a critical number, but it is not a local extrema. We now have language to describe the extreme values and points on a function. We've also acquired Fermat's theorem to help us identify these local extrema.